you're doing the multiple choice, right? Hey. Yep. Okay, make it quick. We're starting.
the exhaust valves close. The operation cycle is then repeated. 3 subsystems feed the engine with fuel and air, and then expel exhaust gases. The intake system, the fuel supply system, the exhaust system. Operate.
Right. Okay, today we're gonna get into ICE, internal combustion engine. And all of us have our opinions about EV and internal combustion engine, but I think even though I'm swapping to an EV, I think I'm gonna be back to internal combustion engine when I'm old. Maybe it's different. The sound, the feel, the fun. Okay, well, we'll discuss how it works. Even though because you are taking a separate course on combustion engine, we're not going to go real in depth. We're going to discuss again the mechatronics aspect of it and kind of an overview how it works. So let's watch this video first, and then we'll discuss in more detail. Right?
Operation of the internal combustion engine, or ICE. The internal combustion engine converts the combustion energy of the fuel inside the engine into mechanical energy. One type of internal combustion engine is the reciprocating piston engine. The vast majority of vehicles are powered by a 4-stroke reciprocating engine. In this video, we will go over the operation of such engines using the example of a 4-stroke piston engine powered by gasoline. We can now see the crank mechanism and the belt timing mechanism. The former is propelled by the energy released during fuel combustion and converts such energy into rotational, mechanical energy. The belt timing mechanism is needed to open the inlet and exhaust valves. It can be put in motion by gear, belt, or chain drive from the crankshaft. For the sake of simplicity, we will only review the operation of one cylinder. The engine's operation cycle consists of 4 strokes, or 2 crankshaft revolutions. The 4-stroke cycle is then repeated. Stroke 1, intake. Stroke 2, compression. Stroke 3, power. Stroke 4, exhaust. During a stroke, the piston travels between 2 extreme positions known as the top dead center and the bottom dead center. 2-stroke engines exist as well, but they are rarely found in cars. Stroke 1, intake. The piston travels down from top dead center to bottom dead center. The cylinder volume expands, creating vacuum pressure. At the same time, the camshaft causes the inlet valves to open, allowing the fuel-air mixture to enter the cylinder. In modern-day vehicles, gasoline is supplied by an injector, whereas in the past, carburetors performed this function. The stroke is completed when the piston reaches bottom dead center and the inlet valves close. The second stroke is compression. This stroke starts at bottom dead center and ends at top dead center. All valves are closed. The cylinder volume is reduced, causing the fuel-air mixture to compress. The compression raises the cylinder's temperature and pressure. As the piston approaches top dead center, the spark at the spark plug ignites the fuel-air mixture. The stroke is finished when the piston reaches top dead center. The third stroke is the power stroke. This is the climax of combustion. The combustion process generates a large amount of heat, and the cylinder pressure can get up to 900 psi. The pressure of expanding gases causes the piston to move from top dead center to bottom dead center and turn the crankshaft by the connecting rod, thereby converting thermal energy into mechanical work. The stroke completes when the piston reaches bottom dead center. The fourth stroke starts at the bottom dead center and ends at top dead center. The camshaft opens the exhaust valves, and the piston expels the exhaust gases from the cylinder. When the piston approaches top dead center, the exhaust valves close, completing the last stroke, the exhaust, and the entire operation cycle. The operation cycle is then repeated. 3 subsystems feed the engine with fuel and air, and then expel exhaust gases. The intake system, the fuel supply system, the exhaust system. Furthermore, normal engine operation necessitates the use of the lubrication and cooling systems. The proper operation of these systems extends engine life. Please keep in mind that we are watching the engine in slow motion. In fact, the crankshaft turns an average of 700 revolutions per minute at idle speed. The upper limit on production cars reaches 8,000 revolutions per minute. Engine speeds in Formula 1 cars can get as high as 22,000 revolutions per minute. You can check the revolutions per minute value on an instrument called a tachometer on your car's dashboard. The operation of the engine begins with the car's starting system. The starter motor starts spinning, engaging the flywheel. The flywheel then stores the energy from the power stroke to use it until the next power stroke. The strokes alternate in different engine cylinders in a certain sequence. This is known as the engine firing order and is required for more stable engine operation. The firing order for this engine is 1, 3, 4, 2. It means that the power stroke occurs in the first cylinder, then the third, fourth, and finally the second cylinder. The sequence is then repeated. Please note that gasoline engines are spark ignition engines, since it is the ignition system, namely the spark plug, that ignites the fuel-air mixture. The primary goal of this system is to ignite the fuel-air mixture on time. Ignition timing is critical to the efficient operation of the engine. There is some time between the appearance of a spark and the complete ignition of the fuel-air mixture and the maximum gas pressure. The piston moves some distance during this time. For maximum engine efficiency, the piston must be within 10 to 12 degrees of top dead center at maximum gas pressure. It means that the ignition system must start in advance. The moment at which the spark plug fires is called the ignition advance angle. The optimal ignition advance angle is determined by crankshaft speed. The higher the crankshaft speed, the earlier the spark plug must fire. If the crankshaft speed is low, the ignition advance angle should be closer to top dead center. In modern engines, ignition timing, fuel injection, and many other tasks are controlled by an engine management system with the engine control unit at its heart, assisted by various sensors. The driver only needs to supply air, which is accomplished with the help of the accelerator pedal, also known as the gas pedal. Please keep in mind that in order to improve engine efficiency, the inlet and exhaust valves open and close prematurely and belatedly related to the dead centers.
Oh, sorry.
The exact timing of the opening and closing of the valves is called valve timing. The optimal valve timing is set during camshaft design and does not change during engine operation. However, if the engine is equipped with a variable valve timing system, valve timing may vary during engine operation depending on the engine operating mode. Fuel-air mixture. The fuel-air mixture in gasoline engines is made up of air and gasoline. The mixture is prepared using a certain fuel-to-air ratio. Ideally, complete combustion of 1 kilogram of gasoline requires 14.7 kilograms of air. But in fact, the engine employs various mixture ratios. The ratio of 1 to 14.7 is the best in terms of power and economy. By reducing the amount of air, we get a more powerful engine but a poorer fuel economy. By increasing the amount of air, we get a more economical but less powerful engine. This range is suitable for normal engine operation. Further changes in the gasoline-to-air ratio will result in increased gasoline consumption and decreased power. Misfiring of the engine is also possible. This concludes our review. For more information on engine subsystems and other topics, watch our next.
Alright, that's a long video, but it gives you a good overview while maintaining some technical details. So let's talk about this a little bit further. Okay, so all these PowerPoints are in the Google Classroom. Okay, so any overview kind of questions about that video? Any particular areas that is most confusing, or you want to discuss more detail? Nothing specific? Okay, that's good for me. So, basic conversion of energy, right? We are talking about maybe about 40% thermal efficiency these days. It's getting better. I think Mazda have the Sky Active. I think it's Atkinson engine, maybe. So they have some techniques. Very lean combustion, maybe somewhere around like 16:1 ratio. Very lean, but they're able to manage the knocking or the combustion temperature. But in general, we're talking about 30 to 40%, maybe 25% 20 years ago. So it's always improving. But we're reaching the limit. I mean, there's a certain point where you cannot really improve it anymore. So pistons, connecting rods, crankshaft, right? So because of the timing of these combustions and the valve is critical, then you're going to need this guy, chain drive. Used to be timing belts in the 90s, 2000s. I don't know whether they're still around. They're still, what kind of car usually?
All the Fords, mostly the Fords.
American cars still belts.
Or even the Japanese.
Really?
Yeah, some of
Okay.
them very very low.
I think more and more are converting to chain though.
Yeah.
I mean, it's just maintenance.
Now for the cord is oil dip. It's
Hmm.
dip in the oil.
I
So
see.
when it what the wear and tear, the small pellets of rubber they get stick into the oil filter. So it's
Ah.
like more for you to replace your engine after some time.
So the thing with belts is just it's not infinite life. Okay, so it doesn't get, it's not as noisy, but you have to replace it, and if it fails at the wrong timing, you got interference engines hitting each other if the belt broke. Because if the timing belt breaks, then you can have the valve opening and the piston coming up. Basically, it's off timing. And then the valve is bent, $2,000 worth of repairs. Okay? Um, so timing belts do not give you a warning. That's the problem. I mean, there is no warning. You just have to replace it after 70,000, 90,000 miles. Uh, you replace it or else, right? But a lot of people are ignorant and they just say, nothing's wrong with my car. And then it breaks in the middle of the road, your engine is trash. So I think timing chain, even though it can be noisy once it starts to wear out, and maybe it has a certain age, it'll still work infinitely. You know, like it'll not fail your engine. So I think timing chain is the way to do it. It also doesn't stretch as much. Um, you do have tensioners to make up for it. We'll discuss that in machine design. Okay, so 4 strokes, 2 revolutions of crankshaft is 1 cycle. It's called the Otto cycle, OTTO. I guess nowadays you have done some variation of it, but that's the guy who invented it. Long time ago. Intake, compression, power exhaust. I don't have to go through again. The video I think did a nice job. The shape of the piston also determines the characteristics of the engine, whether you want a high revving engine or you want a better low end torque. Engines that are designed to do high RPM are usually shorter stroke, bigger bore. So kind of a more bigger diameter, but shorter stroke. Can anybody guess why? Why would that give us a higher limit in RPM?
Let's travel distance.
Less travel distance means, think about limits. Think about the limit of red line, the high RPM limit. What would limit the maximum RPM of your engine?
the weight of the piston and oil.
Sure, the weight. But connect that to the geometry of the combustion chamber. What happens when you go very fast? What's gonna fail? Well, this guy,
The pin is what
okay, the pin, and this guy is going so fast, and then it has to stop, right? And then it goes fast again, and it stops again. So this guy is actually experiencing a lot of acceleration and deceleration, right? And the faster you go, the more extreme acceleration and deceleration of this guy. And what happens when you make the stroke shorter is that you have less, comparatively, less acceleration and deceleration every time it goes up and down. So by shortening the travel of the piston and making the bore bigger instead, you actually have a higher revving piston. But at one point, I mean, the combustion chamber shape also determines the efficiency of your combustion, how good of a flame propagation do you have, okay? Because the flame have to spread. Of course, this happens in like milliseconds, but the flame actually takes some time to spread. And the shape of this guy, if it's too big or too long, is also not optimal. Okay, so depending, whether you want more low-end torque, high-end torque, higher limits in the RPM, then you kind of design it differently. The other thing that limits the maximum RPM is this spring. The valve stem will start to float because see, it also opens and closes like that, right? And if it's, at one point, the valve doesn't have time to sit back on the spring, it's already pushed back again by the camshaft. So the valve have to be lightweight, and the spring has to be stronger while not breaking everything apart. So that's a challenge in increasing the red line. But most people in car modification when you want to increase the red line, the first thing you tackle is the head, basically camshaft, valves. You upgrade those. Okay, so they open intake. Now, the fuel also sprays during this stage. There are direct injection engines. The challenge with direct injection engines is actually maintenance, because this thing actually have the nice effect of cleaning your valve. The valve often have carbon deposits on the top of here. Now, this fuel injector, what's nice about fuel injection system is that it kind of naturally clean that guy. But if you have direct injection, if you inject the fuel into the combustion chamber, like I think a lot of German cars are direct injection also, the valve actually collect deposits and you have to clean that up after like 100,000 kilometers. Here's the spark. Timing is critical. We'll talk more about that. Combustion temperature and pressure. The leaner you go, the higher the combustion temperature, and that's what creates knocking, and also it might damage your piston. Starts to melt your piston too at one point. Power, like I said, the flame is going to need to expand, and the way you control the flame propagation timing is by adjusting the timing. So this is the time for the flame to spread. Exhaust, we talk a little bit about scavenging effect, right? So the speed at which this gets out is critical, and the exhaust valve opening and closing here does have some overlap, a little, maybe a few degrees, not much. Okay? So the intake will have sensors in it. It's called the airflow sensor. We'll talk about that. But you have intake system, you have exhaust, you have the fuel supply, your lubrication systems. I'll talk more about it in machine design maybe, but this oil circuit, the most critical part is here and here, because you need oil pressure to actually sustain. So the bearings are actually plain. Okay, the shaft sits on these two halves of a bearing, and they are supposed to float. Okay, it's supposed to float like that. It's not supposed to sit metal to metal contact. So it only sits there when there is no oil pressure. So during startup, believe it or not, your engine's wear happens not during usage, but actually during startup, during shutdown. That's when it starts to sit on it. So the crank wear happens when you touch. Doesn't happen a lot, assuming your oil is good. And the oil film that creates the boundary layer lubrication has to be the right thickness too. That's why oil has its thickness and temperature ranges. And it also sprays the combustion chamber, but again, this is the deadliest one. You have to maintain oil pressure or else, and then cooling, of course. This entire block has water channels going through it. I have another video on cooling separately. So yeah, that's typical. That's already pretty high. I mean, some economy car probably like 6,500 or like that. My Integra has 8,000 as the RPM limit. Um, the bigger the displacement tends to have lower red line, just because you have more mass moving. So V6 engines, V8 will have lower red lines, just naturally because too many masses, right? Remember, red line is all about lightweight and less inertia, less acceleration, because F equals M times A. And so either you have lighter mass or lower acceleration. F1 cars are crazy. You should hear the videos. It's like, and it ramps up really quick because it has all the lightweight pistons and rods. Like whoop, whoop, whoop. Awesome stuff. All right, we talk about the flywheels. The flywheel is there to actually stabilize because combustion happens at different cylinders, and in between you want the stability of that flywheel. The starter motor just happens to be connected to it. I mean, you don't have to, but it's just practical. Nowadays we have the what do you call this feature? You shut down your engine during traffic.
Auto start stop.
I don't stop. Yeah. Yeah, traffic in Indonesia, really bad. How is it compared to your country? There is no traffic in your country, right?
Have better roads, better traffic. We don't have the cycle whenever we're riding. Yeah.
So obviously you want to fire not in this sequence, so you don't have the shaking. So you kind of balance out the engine vibration. Of course, the ignition has to follow. In the old days, we have distributors, but nowadays it's all electronic to determine which one. The mechanical distributor have these four metals, and then there is a rotor that turns, that touches, and 1, 3, 4, 2, 1, 3, 4, 2, and it's mechanically igniting the spark plugs. Used to be when you have heavy rain and then kind of a flooding, you splash into the distributor. That's usually the first place you go to if your car breaks down during a heavy rain or some flooding. But nowadays, this is all electronic. The coil is often here. Also, it's called a coil on plug system. The coil's job is to increase the voltage, like from 12 volts all the way up to like 20,000 volts, to create the spark at the spark plugs. Spark plugs, they are the one that spark the flame. I don't know whether I capture it. Okay. So this is where you want the maximum pressure to be, like the ultimate combustion is complete, and then it starts hitting the piston, creates power. But in order to create it here, you have to start early, right? And ignition angle is really one of the most critical part in tuning. So fuel ratio, yes, but what then optimize your tune is actually the ignition angle. And your ECU is basically have two main tables, fuel and ignition. So where you are, this is based on RPM, obviously. Higher RPM, then you have to start early. But this table in your ECU is like an Excel table, basically. Is basically the adjustments that you can make for each RPM and each engine load. So you can retard it further, or sorry, advance it earlier, or you can retard it. Usually, when you tune the engine, you basically advance it as much as possible, but not creating knocking. So the more advanced ignition, it creates more power, because then you allow the flame propagation to fully expand. But if you have it too early, then it starts having local explosions before the top dead center, which is bad, real bad. Be careful. You can blow your engine easily if you are too aggressive on that. And that's what the ECU does. Pretty much, it controls the fuel and the ignition. That's its main actuator, right? But the sensors feeding into that is a lot of factors, including like the intake air temperature and all that. We'll talk more about sensors. Okay? Valve timing controlled by the timing chain, but there is also this variable valve timing, which is awesome. Two things that it controls. First, the valve opening, bigger opening for higher RPM, but also the timing. So the timing, how much overlap, is also optimized for the RPM range that you want. So this also helps pollution, by the way. Theoretical, or it's called stoichiometric ratio. You'll sound intelligent if you can say this. It comes from the word stoic, which is, I think it means neutral. So it's balanced. So stoichiometric ratio comes from the equation. I don't remember that. I dropped out from chemical engineering. I switched to mechanical. C something, like C6H, I don't know, man. Whatever. And then O2, right? Combust becomes H2O and CO2, right? But of course you have the pollutants because it's not a perfect combustion. But don't quote me on that. I don't even remember. I think our gasoline are mainly hexane. I'm not even going to try. Chemical engineering dropouts. But yeah, if you do the math on this, the balance is 14.7 to 1. But that's assuming O2 is only 20% of our air, right? Our air contains mostly nitrogen, so this is also only 20% of regular air, which is a mix of nitrogen, oxygen, etc. But all in all, the stoichiometric balance is 14.7 by mass, not by volume, by mass. Okay? So 14.7 air, 1 part gasoline. If you go richer, it actually cools down the combustion a bit. When I say cool, it's not cool, but it's cooler, right? Colder, just slightly colder. So it's more conservative for your engine, especially I'm talking turbo. It cools down the combustion a lot, and so with boosted systems, you actually go to like 12. So you go even more conservative. You want to make more power, go to like 12.5. These are all informed by the oxygen sensor, by the way. So a more lean mixture, of course you save fuel, naturally. You make less power. Even though you know, not that much penalty actually. It's more like a risk. If you go too lean, you're risking the engine, you're creating more pollution, you're creating more NO2, NO3, SO2, SO3, which are the pollutants that you don't want. Uh, so going leaner risks that pollution, and also it's actually a bit harder on your engine, underpowered. But if you're driving like my wife, then it's safe. And you're going to danger of misfiring. Hello. Oh, I think that's the end of my slide. Okay, so let's look at any questions so far. Here's a video on engine structure. I don't know whether you want to watch it. It's also good, I guess. Okay, no voiceover on this. I'll just speed it up. It just kind of show you where things are. We watch all this. Yeah, spark plug wires, camshaft sensors, cooling systems. Yeah, I'll talk a little bit about that. Let me slow it down. So you have the entire block is actually have water channels, but then you have circuits around it for the cooling to recirculate. So throttle body, you have to detect how much you open, because that's going to control the engine load. Idle air control, I think I have this on a separate. Let's just watch this. I have a separate video of this one. Yeah, this is very nice assembly of EGR is exhaust gas recirculation. You actually, it actually helps the combustion a bit by mixing in combustion products. Exhaust manifold. There's your injector, the fuel rail. This is the regulator. I think I mentioned it before. This fuel rail is always under pressure, but the fuel pump actually keep recirculating this. So the way the regulator works is actually once you reach a certain pressure, the membrane opens and the fuel returns to the tank. And so that's how it regulates, right? Using the spring preload. So there is a spring that press the membrane against a hole. So you build up pressure. Once you reach the pressure, the membrane automatically retracts because the pressure pushed back the spring, and then it returns to the tank. And it just keeps doing that. Okay? So it's always recirculating as opposed to pumping into a blind hole. It's not. So this is the return line, or this is the return line, right? And then all the injector does is basically open for a milliseconds. So that's a fuel rail. For diesel engines, it's very high pressure fuel. So the nut sensor, detects, it's basically a microphone. It's a microphone to listen to your engines. And it's tuned for a specific frequency. That's how it detects it. There's a thermostat. We'll talk more about that. Okay, starter motor, oil, the pressure sensor. Okay, here's the accessories. Um, it's quite a few, right? But the big ones are your AC, right? And there is a magnetic clutch on it. If you hear the clicking sound, click, and then the fan starts to sound, and your AC is cold, that's your AC magnetic clutch. The way it works is basically this pulley is always turning because this belt is spinning all the time if your engine is on, right? But the compressor might not be on. And so when this thing is energized, you basically join the two plates between the pulley and the internal plate, the rotor, and then it spins together. So the the electronic magnetic clutch is how you control the compressor to be on or off. Because once the refrigerant reaches a certain pressure, then you disengage the clutch. And then you engage it again once the refrigerant pressure drops. That's the main crankshaft. This is the water pump pulley. Different cars have different ways of doing this. I think my Honda have like an internal water pump rather than an external pulley like this. Of course, you need some idler to keep the tension and keep it wrapped around. We'll talk more about this in machine design. Like you want a certain angle of wrap, and that's why you have this here. Because you don't have to, right? You can go like directly here, but why do you have this guy? Well, sometimes you want the wrap around the pulley so the friction is good. That's alternator, recharge your battery. Power steering, hydraulic power steerings. Nowadays we have electric, so we have less of these things now. Yeah, AC compressor, water pump. Power steering pump for hydraulic ones. One of the earlier ones to fail actually often. Replacing your timing belt is painful. So yeah, I'm a big fan of timing chain. Faster. Timing chain guides, just for it to not rattle as much. That's the oil pump. Is inside. Oil pan, pickup, camshaft, the caps. Again, so these are the bearings that I said. Okay. No balls going around, just plain. Pump oil into it and the shaft floats. Valves, two valves for intake, two valves for exhaust. The spring, so that assembly is going in and out to open and close. Okay, valve stems. That's the head gasket. That's one of the failure points also, the head gasket. If you blow a head gasket, one of the ways you tell is that your oil is mixed with water, like a soap-like, yeah, like a paste, like a toothpaste. That's one indicator of blown head gasket. Because then this is the water channel, and you got oil here, obviously. So you get it mixed up between the oil channels and the water channels. That's the main bearing. Hold your crankshaft, you see? So these are the bearing points. The bearing cap and then from the housing of the engine block. Okay, so it's captured. But you got that hole for the oil flow. So the blue ones are the main bearings. Those. So that's what I said. They are semicircles. Okay, so you have the rod bearings, you have the main bearings. They're all like split halves, circles like that. Three rings. Keep the seal here. Okay. Don't have to talk much about that. Okay, here is the, we can talk a lot more about this. Engine sensors, right?
Modern cars employ a range of sensors to ensure efficient and sustainable engine running. Sensors in different cars may have somewhat varied names and numbers, but the overall operation stays the same. We'll take a look at the most common set of sensors used in gasoline injection engines.
Okay, I'll tell you what. Let's make this a bit more interactive and active learning. Before we get into this, why don't you do a bit of research on how the ECU takes the inputs of all these different sensors and create the output, fuel and ignition timing. Okay, so each of you maybe take different sensors, do a little bit of searching and GPT, whatever. How does these sensors affect the tuning of the fuel and ignition? Okay, I'll let you do that for like 10 minutes. And then we'll discuss it.